galaxies from PHANGS come with all different kinds of structures and morphologies. Those galaxies are disks filled with gas, dust and stars, and they can look quite chaotic, like this example here. In other galaxies, due to the rotation, we see some structures that can form, such as spiral arms, which is in this case. Other galaxies have different features, such as stellar bars, which are elongated features in the centers of galaxies, or various different kinds of rings at various sizes. And those features are known to have an impact on the star formation of galaxies. They can remove gas or compress gas, and if this gas is dense molecular gas, which is the gas out of which future stars may form, then this has an impact on the star formation. So if we want to understand how and especially where stars can form in our galaxies, we need to understand these features better. But before we can do that, we need to actually know if our galaxies have these features or not. So if I want to know if my galaxy has, for example, a stellar bar, what should I do? Well, there's two simple options. The first one is to just look it up in a catalog. There are a lot of catalogs out there where people have had a look at images and classified whether they see spiral arms, bars, rings, or even other structures. So if I'm lucky and my galaxy is on one of those lists, then this can be quite easy. But there is, of course, another option what I can do, which is to classify the galaxy myself. And there's nothing wrong with that, since in the literature these classifications are also based on visual classification. We can try to do the same. The only question here is, which image should I use? Because most of these catalogs out there in the literature are based on optical or infrared images, which are tracing the stellar distribution. But of course we know that in our galaxies there is more than just stars. There's also a lot of dust and gas. So what about using the molecular gas medium instead for doing these classifications? Well, and I should rephrase this question first. Why should we use the molecular gas medium? Well, molecular gas is quite dissipative, so it does respond to the underlying gravitational potential quite well. So we do expect to see features such as spiral arms and bars in our molecular gas medium. But we're also talking about molecular gas, so the dense phase of the interstellar medium, so the gas out of which future stars may form. So by classifying our morphologies based on the molecular gas medium, we can directly try to link the underlying gravitational potential with star formation processes. So this sounds ideal. So let's actually do the survey, which you can find more about in our recently published paper. To do this survey, we need, of course, a sample of galaxies, and we're using the PHANGS-ALMA galaxies. So we're talking about observations at roughly 100 parsecs of 19 nearby galaxies from the so-called main sequence of star-forming galaxies. All these galaxies are nearby and relatively phase-on, and here you can see an example on the right of how they can look like. So we have our sample, and we do have the data, which is also publicly available. So what about a method? We had 10 people out of our team do a visual classifications of our galaxies as they look like in the molecular gas medium, and classify different structures what they see, like spiral arms, stellar bars, and also some ring features. And I won't go into detail about all of them, but just want to highlight the largest ones, which are spiral arms and stellar bars. So for bars, we came up with a new classification just because we didn't really know what to expect from the clumpy molecular medium, because this is the first time somebody has ever done this kind of study based on the molecular medium. So A basically meaning unbarred, and B and C different types of bars. And for the spiral arms, we used commonly used classifications, G meaning it's a two-armed grand design spiral arm, M meaning multiple arms, F flocculent arm segments, so no clear long spiral arms, but rather just segments, and S meaning a smooth distribution in the molecular medium. So 10 people doing this. What is the result? How do spiral arms and bars look like in our PHANGS galaxies? Well, you are already looking at one of the results, because this picture in the background actually encodes our classifications. So on the left you can see in purple whether the galaxy is classified as barred or in red unbarred, and on the right you can see the spiral arm classifications, so grand design in purple, multi-arms in yellow and flocculent in red. And you can also see that there is a lot of galaxies colored in gray, which is just galaxies where either the data quality was not good enough or the people couldn't come to an agreement. So we dropped them from any further analysis just to make sure that any statistics we are doing is based on galaxies where we are sure that we're seeing those features and the data quality is also good enough. Okay, this is already one of our major results, but of course we want to do a little more. All of those galaxies are on the main sequence of star-forming galaxies. So we're talking about the global star formation rate of a galaxy as a function of its stellar mass. And if you have a look where the bars are distributed here, we can see that bars in green are at higher stellar masses compared to the unbarred galaxies in purple. This is an agreement with some literature studies based on the stellar distribution, but not with all. If we now have a look at spiral arms, we can see that our grand design spiral arms in orange are at higher stellar masses than the flocculent galaxies in purple. And now it is also unsurprising that most of our grand designs are in barred galaxies compared to the flocculent galaxies, which tend to be in unbarred galaxies. Well, this has been found in the literature based on the stellar distribution as well, but scientists are still not sure what exactly is happening here. So this could be just a coincidence because both features appear more commonly at high stellar masses and they just coincidentally overlay. But it could also be that, for example, the presence of a stellar bar can trigger the formation of a spiral arm. However, studies on this are still quite inconclusive, so stay tuned for some future updates here. In generally, we can say that most of our classifications agreed quite well with literature classifications from the stellar distribution. There are a few outliers here. If you want to know more about them, you can check out the paper. One last thing that I want to talk about is one of the major advantages that we have when having a look at the molecular gas medium, which are so-called bar lanes, which you do not see in the stellar distribution. So, what are bar lanes? Well, generally, a stellar bar consists of several orbits, like these X1 and X2 orbits. And this is why we see this elongated feature in the stellar distribution as they follow these orbits. However, gas, on the other hand, will be funneled along the edges of these orbits, as you can see in this example here. So gas gets funneled to the center and can accumulate in a ring. And this is also why the bars do look quite different in our molecular gas medium. We do not see one elongated structure, but we actually see two lanes with an offset in the center. And these so-called bar lanes, here's just two examples of how they look like in our medium. And you can see the left case pretty much looks like the comic. So we have two straight bar lanes with an offset in the center, but on the right we already see different examples. And this already tells us that there is quite a variety of different bar lane shapes and morphologies in our sample. And we actually try to classify this, so classify the appearance of these bar lanes in our molecular gas medium. And one of our findings is that bar lanes that tend to be short in the molecular gas medium. So in the molecular gas, the bar lane seizes close to the center and does not reach to the outer structures such as spiral arms. These kind of bar lanes tend to be more curved in shape. On the other hand, we have bar lanes that tend to be fully covered in molecular gas. So the bar lanes seem to connect to outer structures, like the example on the bottom right here, and they tend to be straighter in shape. And this is actually correlated with the global molecular gas mass fraction. So the more molecular gas there is available in the whole galaxy, the more is also on the bar lanes and they tend to be straighter. We also see a weak trend with bar strength here, but the statistics is not too good here, so the uncertainties are quite large. Basically, we don't see a strong bar that looks like the left case. This is similar to what was found by Kommer in 2009 based on observations on dust, where you can also see these bar lanes quite nicely. The statistic is not too good, so take this with a grain of salt. But what we can take away from this basically is that potentially we might be able to make assumptions about the global content of molecular gas in a galaxy and the strength of a bar by simply having a look at how the bar lane looks like in the molecular medium. And with that, I hope I could convince you that in the molecular gas medium, we're able to trace features such as spiral arms and bars quite well. And we also have one advantage, which is that we see these bar lengths nicely, which enable us to do some novel studies about the shape and geometry of bars in general. With that, I say thank you very much and see you next time.